Good day everyone, welcome to this video. In this video I'm going to be showing how to code a PID controller routine for a DC-DC converter. In this example, a boost converter will be used, but the same code could be used on other types of converters, a buck, a flyback, whatever type of converters. The boost is just used in this particular example. And essentially this serves as sort of a way to code it. In this example I'm using a PIC 24 FJ64GA002, specifically because this controller is available in the Proteus library, so I can easily test and check that the PID algorithm works, is functioning. But for real application for closed loop control of a DC-DC converter or any other type of converter, um, basically a DSPIC is a better resource to be used. So essentially what this video is just showing how to go about the coding process. Obviously you could use this microcontroller as well for it, but just to know there are better options out there. But this video just shows a code breakdown, sort of an code structure algorithm, if you will, of how to implement a PID controller. So essentially, what the goal of the PID controller is basically to have a fixed voltage or current on the output. So in the case of a voltage mode controlled converter, you want the voltage to stay constant irrespective of the output current of the system. And for a constant current output, you want the output current of your converter to stay constant, irrespective of the voltage of the load. So the voltage of the load is going to vary, but the current going into it is going to stay constant. So that's what this video deals with: fixed voltage or fixed current. As for average current mode control, that's in a different video entirely. I'm gonna link. That's a different type of code. Coding that is a different way from, just fixed voltage or fixed current, or sort of a battery charger. That's also a different type of way you have to code that. This video just covers mainly just the PID for fixed voltage or fixed current. Alright, so let me just go to next. So there's a really nice document I found on the internet where it describes a digital PID controller routine. This is the link right there, right here. I'm gonna link to it. Obviously I can't open that document on this video. So that's that. And so just jumping right into it. So the basic form of a PID controller is this equation right here. Just a brief introduction before I get started and anything else. So okay, let me just remove these two for now. So the basic form is this, right? PID is going to be the proportional component multiplied by the error, the integral multiplied by the summation of the error, and derivative constant multiplied by the change of the error. So this particular form is a position form PID. So there are two forms of PIDs. There's a velocity form and there's a position form. So for DC motors, I find position form works just fine, but for converters, for DC-DC converters that have much faster loops, control loops, the velocity form is much better to use. So now I'm just gonna put what I delete, what I removed, and just put them back. So if you look at this first line here, that's the position form of a PID controller. So as you can see here, it's the KP. Ignore this I. This I is to indicate is for the current, and this is the error. This is the initial error that's calculated right now, right before the step, and this is the KI component, and this is the summation right there. And obviously the KD, and now this is where you see this is the current. This is the current error, and this is the previous error. So after each execution, you essentially have to equate 1 to 0, because this is the previous error and this is the present error. It will make much more sense when I show the code in entirety. But that's the position form. And as you can see there, you kind of have to keep track of this guy. You have to sum the error yourself. You have to sum it. But in the velocity form, it kind of turns that on its head. Kind of changes that, actually. So what what you have in the velocity form, you essentially have. So this is the PID output, the current PID output. So in the velocity form, you have delta, something like delta m will be equals to this particular one, the PID minus the previous one, right? So this serves as a brief introduction to it. I don't want to get too much into the theory. You could just go read that document for that, and it shows exactly the math and everything for the velocity form of the PID. But it works much better because the error tracking is done intrinsically in the equation. You don't have to do it separately like in the position form. And the position form has a tendency to kind of how do you say, integral wind up. It has a tendency to do that. So let's say you have a system where you're sort of ramping it up slowly, you're ramping up the input power slowly. The position form would absolutely not work for that, because by the time you actually get to a point where your converter can get to the set point, it's racked up so much of this particular value, it's like ridiculous. Like, it's gonna take forever to actually come down. So it, how do I say it, like, so let's say your set point is about, like, for a boost converter, let's say your set point is like 26 volts in the output for an input voltage of 15 volts. It will get to 26 volts just fine. But let's say you changed your set point to say 20 volts. It will take a really long time to actually go back down to 20 volts. Whereas for the velocity form, a PID controller, it will do that pretty quickly. Um, because of some of the qualities it has. And the downside for the velocity form is that, well, the equation's a bit more complicated, but it's the benefits are much more. So this is the equation. Once you compute this particular part here that I highlighted, you come up with this equation here. Let me just try to get it on its own. And alright. So this is the equation on its own. You have the Kp, Ki, Kd multiplied by the current error 0, and then the Kp multiplied by 2 multiplied by Kd. I know it seems like weird, where does the 2 multiplied by the Kd come from, but just look at that document. It's literally just math. It's just the equations. Once you work it out, it give you this equation right here. And multiply by the previous error. And now in this case, another disadvantage is you have to keep track of two errors. So whereas in the position form, you only had to keep track of the previous error and the current error, this one you have to go two places back. So you have to the previous error and the previous error, basically, which is what this is. And also you have to keep track of the previous iteration. So this is where the summing component is intrinsic into the equation. It's the yeah, where it becomes intrinsic into the equation. So this is the previous PID input, and yeah. So this is the basic equation. Now let me just go down to the code and explain the code. So the code is basically um, I used MPLAB code configurator for it because it's a lot easier to do that with it. And all you have here is ADC. You have two ADC terminals, AN0 and AN1. And then you have OC1 output capture 1, PWM mode on OC 4 pin is disabled, and timer 2 is being used as the source for it. And we look at timer 2 there, the switching frequency in this example is 100 kilohertz, and I find the 100 kilohertz to be a really nice frequency to use, because you get a nice it's a nice balance between the speed. So your settling time speed will be a lot more. It'd be better because now you can actually make your control loop, your sampling time for your ADC. Well, let me say control sampling frequency. Yes, sampling frequency. Like what I mean is, how often are you changing the duty cycle whilst you're doing the closed loop control? So, because this is 10 microseconds, we could literally make that loop as fast as 10 microseconds. Obviously, this microcontroller is not designed for this purpose, so we can only go as far as 150 microseconds. And in the real world application, if you're not doing it on like a professional PCB, like a PCB where there's like a solder mask on it, and it's not, the PCB is not acting like a giant antenna, you could make the loop a lot faster than this. Now in this case it's 3 milliseconds, but if you have a real professional PCB, you could make this, you take this down to 200 microseconds. Obviously, in the simulation here, I could take it down to 200 microseconds, but in reality, if you did a DIY PCB at your place, at your house, and you're implementing this, 3 milliseconds is fast enough. Obviously, it won't be like professional level, getting to the settling time or professionally made product or whatever, but it would work. Um, and you don't want to have those kinds of problems, because in the real world application, if the loop is too quick, then you might have other issues, because the hardware is essentially limited in that aspect if there's no solder mask on it. So anyway, so that's timer 2, that's 10 microseconds. But also another reason why we make the switching frequency very high, not very high, but reasonably high, like 100 kilohertz, is cause the component sizes can be a lot less. And if your capacitor size is a lot less, it means you can get to your settling time much faster. You have a lot more flexibility control wise with your coefficients, so there won't be a possibility of it going unstable. Whilst with a big capacitor and a big inductor, you kind of have to be careful, because you can't, because they take time to discharge, and that time you have to take into account whilst you're doing your control, whilst you're choosing your coefficient. You can't make the coefficients too high, they have to be super low, because you have to basically make the integral part super low, so it doesn't add on too quickly, because we're leaving some space for the capacitor, which is so big, to actually discharge. So having a switching frequency of I'd say 60 kilohertz and above, it's a big advantage. Personally, I'd go above 60 kilohertz, at least 75. Personally, for me, at least 75, but 100 kilohertz is a sweet spot. And if you design your PCB decently, alright, it should function just fine with 100 kilohertz. With 60 kilohertz and below, it gets you kind of have to have bigger components on your board, and your control suffers for it. You don't have a lot of flexibility control wise. And then timer 1 is essentially for the loop execution times. So the interrupt, this is basically a timer interrupt. So basically your PID control loop control, the algorithm is gonna occur every 3 milliseconds in this case. And this, of course, you can make it as low as 10 microseconds theoretically, but with this microcontroller you can only go down to what I checked, you could go down to 130 microseconds, but safely with a proper PCB, I'd say take it down to 200 microseconds and no more, for it to function properly. You want to give yourself some breathing room. Alright, so but like I said, there are better microcontrollers out there that could do better than this particular one, but this could also work just fine. And this is just for the you are to sort of see the current and voltage levels, just in case your ADC is not working, and etc. Alright, so don't get too wrapped up into this part. This part is basically for people that want to use a PIC to code a PID controller routine for a DC-DC converter. But Texas Instruments and STM actually have really great packages, controllers to do this at a much higher level. So if you want to do that, you can do that. The DS PIC also has one that does that to a really high level, but it's not this particular microcontroller. But this part is basically for those that want to use the microchip for that. So if you're not going to use the microchip to implement your routine, please skip this part. Just focus on the part where I'm explaining the code. Alright, so now I'm just going to go into the timer 1 part. So this is the main part, I guess. So in the PID controller routine, the first thing you want to do is obviously these are the variables, the VREF. You have the VREF here, which is the reference voltage, obviously the current reference, and this is the actual, what you actually sensing from the pins, the I actual, the V actual. So the voltage sensor is connected to AN0 and the current sensor is connected to AN1. And this is extant float control. This is basically for the PWM, I believe. I don't think I'm actually using this variable extant float control. I think that's why it's underlined, in fact. So it's not being used. And this right here is the float array for the voltage. Constant voltage control, and this is the array for constant current control. So this is for the error. This is the error array, and this is the output to the step. You know, the step, the PWM step. So in this case, it would be this. It represents this, or in the traditional terms, I guess, would be this PID, the input. That would be for the PWM that's gonna be going to the converter. Alright, so that's that. So this has been initialized in the main, so this is why it's external everywhere there. And here you have the calculation of the V actual, and here what you want to do is this, right? So the basic way to do this is the simplest way I know to implement a voltage sensor, basic one anyway, is to use a voltage divider resistor, using two resistors. So you have a big resistor and a small resistor, right? So let me just show the Proteus. So something like this, right? So you have a big resistor and you have a small one, and then this goes to your ADC. So essentially, how do you make sense of that in your microcontroller wise? So you go here, and so ADC1 buff 0, that's basically this guy. So also with the ADC, well, in this particular example, let me not get too deep into that. For this particular PIC example, right? So this ADC1 buff 0, the ADC is operating in scanning mode. So what that means, basically, it constantly scans the channels and just records whatever value it gets and just plugs them into ADC1 buff 0 and ADC1 buff 1, right? So that's obviously AN0, AN1, or whatever in whatever order you select them to be. And then you have to, in this case, you have to select scan enable here, tick them off, and there you go. You have them, everything working just fine. And for calculating the actual voltage from the resistor divider setup is this formula right here. So first up, the first thing you want to do is you want to obtain the actual voltage, right? The actual voltage that your microcontroller is seeing. So this 5.0 right here is the VREF. So let me just put a comment there. ADC rep, let me just say ADC rep because I'm already using B rep. So ADC rep is equals to 5.0 volt. So it all depends. Sometimes the microcontroller has a ADC ref of 3.3. So if it's a 3.3 volts microcontroller, this is going to be 3.3 volts. And this 1023 is a 10-bit ADC, right? So that's 2 to the power of 10 minus 1, because the maximum value is 1023, not 1024, that your microcontroller actually sees. So that's why this is 1023 and not 1024. So that's for 10 bits. So for 12 bit, that will be 2 to the power of 12, which is going to be 4096 minus 1, which is going to be 4095. So so that's 2 to the power of 10. Let me just use this. 2 to the power of 10 is equals to 1024. So that's why you have 1023 there. So after you've done this particular step, now you have the voltage that your microcontroller sees, right? So after that, you need to know what that voltage represents, right? Because you're using a resistor divider, right? You have to scale it back up, and that's what the next one does. So basically what you have here is the bigger resistor plus the smaller resistor divided by the smaller resistor. You have to multiply it by that voltage that you got. And if you do all of that, so basically if you say 5 divided by 1023 multiplied by this right here, you get this here. And basically I don't include these two lines in the code. I commented them out for code execution time because it's just gonna take a while, because remember this is like almost like a digital control loop. You want it to be as fast as possible because you're competing with the analog equivalent, which essentially has no delay. It's basically continuous. It has a delay, but it's negligible. So essentially trying to get this to sort of mimic that. So that's why I just made it to be one line. And it's the same thing for the current control as well. So in this case, in this particular example anyway, um it's ACS 712 controllers being controller current sensors being used, a 20 amp variant. So that's what's being used in this particular case. Same thing as the first time. Try to get the actual 80 voltage that your microcontroller is seeing, the actual voltage, and make the appropriate changes. Sorry, why am I highlighting? And make the appropriate changes in terms of your ADC ref and resolution. Um, your ADC resolution. If it's 12-bit, change that accordingly. If it's not 5.0, change that accordingly. And obviously, if you look at the data sheet of that current sensor, you notice a baseline value of 2.5. Depending on how you connect it, right? It states that in the data sheet. The value is either going to be higher or lower. If you're working with a 3.3 volts microcontroller, I suggest you connect it in such a way where the value it reads is always going to be lower than 2.5 volts. Just make sure of that. Obviously you can connect it the other way, but I encourage not. Usually they're made to connect the other way in terms of like you want to sense like an AC current or something like that. So where the readings you get is actually more than 2.5, and find out what the baseline value is. Sometimes it's not 2.5, it's like 2.45, 2.4 in fact, with a really weird sensor. And so anyway, so up to that you do this next computation, which is 0.1, so it's basically 100 millivolts per amps. So that's why this is 0.1. And others, I think the 30 amp variant, it's 66 millivolts, so this would be 0.066 in case of that. But in this case it's 20 amp variant, so it's 0.1. Yeah, and yeah, that's that. So 2.5 minus actual, and as usual, I'm not trying to do all this every time, so just make it quick with one line of calculation and done. Everything's done, and that's the end of your sensor stuff. There's the voltage sensor and the current sensor. You could also get a current shunt. Obviously you're gonna have to figure out what the scaling issue is there and modify this part here if you have a current shunt. Obviously you have to modify main thing you have to modify here is this guy here, is the gain. This part stays the same because you're literally just getting the voltage, and the next part you have to change this part right here, this part. And for different resistor voltage ratio, remember 1200 big resistor, 50 small resistor, right? I assume you want to step down the voltage before you send to your microcontroller. So well, let me not use that word big resistor and small resistor. Let me say R1 and R2. Okay, say R1. R1 is the top resistor that's connected to the voltage source you're trying to sense. And R2 is the small resistor. I'm not small, say small. Is the resistor that of which the top part you connect to your microcontroller. So that's 50. Actually, in this particular scenario, it's 1.2 mega ohms K, and the second one is 50K.
but there's no point writing that here. I mean, it's just multiples of 10, so you can cancel out. So that's that. And so this is actually the sensor part. And also, another thing I want to take note of is if you're doing something like this, right, you want to make the smallest sensor quite large, like at least 50K. If you're really trying to push it 10K, anything below 10K for the small value, yeah, I don't know. It's I don't advise that. Try to make the smaller one a bit larger because you don't want your sensors to start taking power away from your converter. I know it's a tiny bit of power, but for this particular resistors, I'm guessing you might be using quarter watt resistors. They get hot. They get hot because literally it's quarter watts. They can't take more than that, and you don't want your sensors getting hot because once they get hot, the resistance changes, and then basically this reading you're having here is basically useless. Because can you imagine the resistance? This resistance just going to like four. Okay, it actually increases, going to like 60 kilo ohms. Because when they get hot, they increase most of the time the resistance. This goes to like 60 kilo ohms, and then your reading is like it's like wrong, and then your converter's output voltage keeps increasing because it's seeing something wrong here. So always try to choose a resistance. Always try to choose a resistance value right here that's like small. No, sorry, not small. Like large. Like large. Like personally, I like to go for like 100K. You know, below here. 50K is okay. Or trying to think of a standard value around this here of 47K. Yeah, 47K is a standard value. That's okay. Try to make it higher, and so that your losses through the resistor, you can calculate your losses, power losses. It's v squared divided by r, so the v across the resistor divided by square root of that divided by your r. Try to make sure that's like a lot lower than quarter watt. Like I mean a lot, like 10 times less than quarter watt, just to be safe. Because once it starts getting close to quarter watt, they start to feel warm a bit, and once the resistors start to feel warm, that's a huge problem. You do not want that. That's a bad time for control. So the code, remember, the code will always stay the same. It's the hardware that kind of changes. The hardware gets issues, you touch it, you do this, and all these things, and things change, but the code stays the same. Anyway, so that's that for the voltage stuff, the V actual. So that's how you calculate the V actual, and that's how you calculate the I actual. Um, yeah, and this is the same across all microcontrollers. Obviously, other microcontroller you would have a different um, register where you actually find it. I forget which one it is for STM. I'm not. I don't know which one it is for Texas, but you have to find out what where they store in the ADC. It's probably in some sort of buffer or register. Um, you have to obtain that value, and if it's STM or TI, it's gonna be 4095 over here, and 3.3 volts here, depending on which variation of those microcontrollers you're making use of. But essentially, this is just how you obtain your actual voltage and actual current from your ADC readings, which, as you can imagine, is very important. It's very important to obtain these readings, because if you don't, then you know there's no point in doing control. And now I'm just comment this out. This is the current control part. I want to kind of touch on the voltage control first, and then this afterwards. All right. Um. So so this is the voltage control. So first off, what you want to do is you want to equate the previous control move to the current one. So obviously, once you start off, this is like 0, 0.0, so everything would basically be 0, 0.0. But I tested this a couple of times. When I actually put this below over here, it gave me quite a bit of issues. So I prefer that you just do it, put it in this order. So, because this order I know works for sure. So this order is because the order for velocity form PID control, the order in which you actually execute it actually matters. Unlike the position form where you can just put it anywhere, but here you have to put it in this order. So the previous error equate the previous error, um, two errors ago, if you will, equals to the previous error, and the previous error equates to the current error, right? And now this is computing the actual error, the error calculation, which is VREF minus V actual, and here you have MVO, and then you basically have the equation. This is basically just steps. So it's this is the PID control step. Obviously here KPB multiplied by KI plus KD, and this is the step basically. Um, and then afterwards you want to limit the duty cycle. So here you have control max. This is the max duty cycle. So if this value is greater than the maximum value, you have to equate it. Basically, we're just limiting duty cycle. You equate it to the control max. Else, if it's less or equals to the minimum, which is 0.0, you do not want this value going negative, because that will create all kinds of problems. So you equate it to the control min, and or else you just leave it the way it is. This else part, yeah, that's the part that gets executed the most, because it rarely goes higher or above, unless you're ramping up very slowly. You're ramping up your input very slowly. So, and this is the OC1RS. So that's for the PWM. This is when you actually plug it into the PWM. It's important to do this before you do this part here. So this is the final part. Once you do this, there's no going back, right? So this is the max duty. So the max duty is as you can imagine, that's the duty cycle, maximum duty cycle for switching frequency of 100 kilohertz for this particular microcontroller. Obviously, for other microcontrollers, it will be different. And also, there's also something important that I have to state. And yeah, you multiply by this. So you multiply the max duty by this, and there's a reason for that, because the way this controller is coded, the maximum output value, which is this, is 1. There's a reason for that, because when in the modules that I've done in the past, talking about control, we have always assumed that the maximum output is always 1. So I try to bring that same energy into the code, because I find that the code is a lot more stable when I just make that assumption that this maximum value is 1. So, and this code is a lot more scalable that way, so you can use it on another microcontroller with a different PWM resolution, and you don't have to worry about changing these coefficients. You could just use literally the same coefficient. All you have to do is change the max duty cycle. So how do you get this max duty cycle? So you have to go to timer 2 there. Obviously it will be different than other microcontrollers, but okay, I have to zoom in. There. As you can see here, the period value is 159, right? So basically 159 represents 100% duty cycle, and that's what is up here. So this is where the coefficients are. Okay, let me just remove this, just comment that out. Alright, so this is where the coefficients are, right? And max duty is 159. In this case, I reduced the duty cycle to 0.8, the maximum. The minimum obviously 0.0. So in this case, maximum duty cycle is 0.8 out of 1. 1 representing 100% duty cycle. So in this way, all you have to do using another microcontroller is you just have to change this particular value. Now this is where this microcontroller is lacking a little bit. You find DSPICs, this max value for a switching frequency of 100 kilohertz. This value here is about like 600, if I remember correctly, or 6. Yes, it's over times 4 of this value, which is a lot more PWM resolution. And if you look even at some STM and Texas microcontrollers, this value goes up to like 1,000. 1,000. Actually, there's a DSPIC where this value goes to 1,000 for 100 kilohertz. It's a really good one. And there you have more resolution, and you could use the same coefficients. You don't have to worry about changing the coefficients heavily, because it's basically the same thing. It's a max of 1. The PID just outputs a max of 1. It doesn't go past 1. So it's like almost like unity. And after that max of 1, you have to multiply it by this, obviously, to scale it to the proper, um, how do you say, proper duty cycle for the microcontroller, right? And now for the coefficients, and I think this is where it kind of gets a bit weird and confusing. So just basically, I use these rules when doing this. There's a way to calculate them and to try to get your loops quite stable. You can calculate it, but I mean, there's several ways to calculate it out there. I'm not gonna get into that in this video. This is how I usually do it when I'm trying to code for a PID controller loop. I usually use this rule, um, general thumb sucked tuning rule. Um, I don't know, you might be discouraged, but this is what I use. Alright, so the basic idea is to just start the values low, right? Start them quite low. So for the KP is the gain, the KI is the integral, and the KD I find for power supplies, digital control loops, DC-DC converters, the KD does not really have that big of an influence on it. So I usually just make it 0.0, because if you do change the KD too much, it's gonna ruin your controller. So better not, especially if it's thumb sucked, better not do anything with the KD. Just leave it at 0.0. Usually a PI controller for digital control loop for a DC-DC converter is good enough. It's more than good enough, actually. Um, Obviously on a professional scale, you have to kind of get more, I don't know, get more specific with the control scheme, like a pole zero compensator. But this is for a basic prototype. Alright, so a PI controller is usually good enough for that. So you start your values low. So I start them here. You notice when I run the spice analysis in Proteus now, you notice it's quite slow. So you might have to change it for your specific application, but I prefer it to be slow at first. As long as we get to the set point, then I know I can make it faster. So essentially, to make to decrease your settling time, you have to make you have to increase your integral component. This is the main part. This is the part that literally it increases it lets you set it basically helps you reach the set point faster, the KI component. But here's the kicker. This is where tuning gets a bit, I guess, tricky. Um you you cannot increase the KI. The KI cannot be too close to the KP value or it gets unstable. So as you increase the KI, you sort of have to increase the KP proportionally. And here's the other kicker. The KP cannot be too high or everything will go unstable totally. So there's like a narrow, so not a narrow window, but there's like a window there where you can increase the KP, where you can increase the KI to make it settle faster. You reach the settling time, decrease the settling time, help your let it reach the set point basically faster, much faster. Basically, you're increasing the KI, and then you have to increase the KP. Once every time you increase the KI, you have to increase the KP um, by a certain degree. So let me put it this way, right? So you must always try to maintain um, the KP should always be at least 3 times bigger than the KI. Just keep that in mind. It should always be 3 times bigger than the KI. Sometimes it can be 2 times bigger, but I usually don't like to risk that. So I just like to keep the KP 3 times bigger than the KI. So in this particular scenario, let's say it's too slow, right? So what you do is you'd increase the KI slightly and increase the KP proportionally. So after you get to a certain point, right, the settling time will be faster, right? You have faster settling time. But once you get to a certain point, you might start to notice oscillations, right? So once you notice oscillation, now you have to take it back down. You have to take your KP back down and kind of make your KP to be like 2 times bigger than KI. Alright, so now I'm gonna say all of that and not be so confusing. So again, I'll say it again. Actually, I need to change these text values. So first off, let me just actually type this out to help me keep track of what I'm saying. So ki um largely affects settling time. So what you want to do is increase ki and increase kp to be at least three times of the ki. So you have to constantly do this, and if you get to a point, if you um, reach unstable point, like you know when your system's unstable, like it starts to oscillate, etc. When you reach an unstable point, then you have to take kp down just a bit, and now your new reference is you're gonna make kp only um, 2 times of your ki, basically. This I find works as well, but no more. No lower, because if you're dealing with a system with voltage and current, you don't want to play too much. So just try to be conservative with it. Don't be aggressive, because you literally burn your compound, your parts if you're too aggressive. So just keep it safe. Like here, usually this is better. Um, Even though sometimes you might compromise, you have to compromise on the speed sometimes, but it does get to the set point, and that's fine. And your disturbance response will be kind of not great, but at this point it will be much better than this, right? Because your more ki is better for the system to a certain degree. So you have to understand the fact that both of them could make your system unstable. The ki could make it unstable, the kp could make it unstable, but the entire system is more sensitive to the kp than it is to the ki in terms of instability. In terms of speed, it's more sensitive to the ki than it is to the kp. I know that's weird. It's weird the way it is. I feel like theoretically it's okay. It should be the other way around, but actually it's like it's the way it is. It's so speed wise. Let me type that. Speed wise, um, system is sensitive to ki. Stability wise, system is more sensitive to kp. By instability, I'm talking about like your output voltage or output current doing this, just going up and down like a zigzag, giant, giant. How do you say it? Um, Ripple, like giant ripples. You're gonna be seeing that. And speed-wise, it will just with the regards to the ki, it will get there faster. Obviously, for pi, for like PFC, power factor correction, you want it to do that. You want your ki to be very big. So it's not gonna be 2 times ki for that one. It's gonna be closer, I guess, because you want your ki to be much bigger. You want the system to be kind of crazy. You want the disturbance response to be off the charts, to be very sensitive to disturbance and be able to react very fast to disturbances. But this is not um, a super dynamic system like a power factor correction. This is just DC-DC, so try to keep it stable. So anyway, I think this is better than the one I have there. Those were just previous notes, and just delete that and paste this there and comment. Alright, so just keep this in mind as general tuning parameters. And I always start my KP at 0.002256. Personally, on other microcontrollers, like not other mic on other how do you say it, another on other converters that are not boost, start your KP at this 0.0003. I know it's kind of overkill, and your KI at least 3 times less than that. So to make sure of what I'm saying. Yeah, 3 times, 4 times. So you should keep it like 4 times less, or 3.5 times to 4 times less than that. I know I said 3 times, I got the math wrong. But let me just say 3 or 3.5 to 4 times. So this could be 0.00075. Actually, another zero there. So now this will be super slow. Okay, let me not say super slow, it will be slow. And then what you can do is you can start to increase this a bit. Obviously, then you have to increase KP proportionally as well, and be careful. Watch your system. Make sure it's not getting unstable, because remember, you go high with the KP, too high with the KP, then it will have issues. So once you hit that point, you just kind of stop the KP. You pause the KP where it's at, and then you increase the KI independently of increasing the KP until it's here. And then once it's here, please stop. Well, you can continue. It's your system. It's your, I guess, your system to burn. But normally, I think you should just stop right there. All right, that's that. I think I should zoom in more visible. And that's that. Basically, that's how you choose your coefficients. It's the same for current. Obviously, for current, it's about a bit more. I guess I went a bit more with it, but that's the way it is. And that in essence is a PID controller for a voltage. That is a PID controller. Yes, the that's the way it is. So now I'm just gonna run it and do a spice analysis. So now in this particular case, the VREF is selected to be 60. VREF is 60, the voltage set point. I'm just gonna go to purchase, and yeah, that's the point. So the input in this case is 50 volts, and output here is 10 ohms, and it's just an example, obviously. And like I said, um, usually when you calculate the voltage and current values for these microcontrollers, as for these converters rather, when you calculate the capacitors, and the capacitor values and the inductor values, they are usually low for high frequency converters. And sometimes with the capacitor, you might get a value of say 5 microfarads or 3 microfarads. And I know the original thought is, oh my gosh, that's so low. No, it's not. It's actually good value. If you're gonna increase that value, try not to go more than 3 to 4 times of that value, because once you go past that, then you might have issues, especially in a case where you have a continuous current load. If it's a continuous current load, it's fine, believe me. That value you calculated is fine. Obviously, you have to go more than it to take into account parasitic resistance, and you have to parallel the capacitors to reduce the parasitic resistance of the capacitor, and you have to like go 3 4 times higher, I guess, or sometimes 2 times is okay, but do not go so high, like, I don't know, to the thousands or the hundreds. Obviously in this case I have 100 microfarads, which is quite high. If you're gonna go crazy, don't go past 100 microfarads, because it will compromise your control. It will compromise it heavily. So this right here, this process that I described up here, it gets a lot more tedious, because you have to go a lot lower. You might even have to go lower than this. Can you imagine that? Going lower than this value here, and having to wait seconds for your system to get to the set point. That's a nightmare. So just try to, with this value, with your capacitor value here, try to limit to 100 microfarads. I know some topologies require you to go to the thousands. That's a special case. If it is indeed that case, then I'm sorry. You have to start very low here with your KP and your KI values. But if you're dealing with like a regular buck, a regular boosted chook, or a flyback or something that does not require too large of a capacitance there, like what the capacitor you calculate for it is a low one, that is a good thing for control anyway. And you might be thinking, oh, the ripple is going to be ridiculous. No, it will not be ridiculous. It's just the math, it's just the converter. It's going to be fine. So 100 microfarads is more than enough for this particular example anyway, for 100 kilohertz. And yeah, so that's one thing I wanted to point out. So now I'm just gonna run it, make sure that it's running this particular one, um, and go to the controller there. So this particular controller is operating at 32 megahertz, and yeah, obviously this is the gate for the gate, 10 kilo ohms. Gate resistor, pull down resistor. Alright, so now I'm just gonna run the spice analysis. Might take a couple of minutes. Alright, it's going really fast. I don't know if that's a good or a bad thing. I guess I'm gonna see based on the results. Anyway, so just go back to the code. And for the current, is essentially the same thing. Only this time we're using different arrays. So now it's gonna be MI instead of MV. And you might already be thinking, in case of using a battery charger, you could have if statements that switches between these two. But for battery chargers, I prefer to use a double loop system instead of individuals like this. I kind of prefer to just use individual loops like this, um, individual control routines, um, separate in situations like this. Or in case of if I was to use it with a battery charger, I kind of only want to use it as a last resort, not as the first not as the first solution. The best solution obviously for those is to do a double loop, like average current mode control. Obviously it's not average current mode control for a battery charger, it's a bit different to that. Well, the one I like to use for that is a bit different from average current mode control. Similar but different. Um, so let's see, is that done? Let's see if there's a issue there. And there it is. As you can see, it's quite slow, but it does get to the set point, and the set point in this case is 60 volts. It's about 59.8, and it's going to jump up and down. Obviously that's a consequence of the PWM resolution. There's no perfect duty cycle for 60 volts in this case, so it's just gonna fluctuate up and down like that. And there you have it. So that's 60 volts on the output for and obviously as you can see it's a bit slow. I know this is what it gets to the settling time at 190, but in terms of digital PSUs, that's slow. It should be in the microsecond ranges, to be honest. But in this case, it's safe. You won't even notice this, right? In a basic example, so for in terms of something like almost like a teaching moment to sort of understand how this works, this is just fine. Obviously, you can make it faster if you want, by tweaking it, like I said, by increasing the Ki and increasing the Kp proportionally as well, until obviously system goes unstable. And keep in mind, it looks like this because the capacitance is high. Let me show you an example. Let's say I make this 10 times more. See what happens. Um, it might still settle, but I'm not counting on that. It might reach the settling point, but the signal might look a bit more interesting. So keep this, the way this looks in mind. Keep in mind that's just inrush. This right here is just in rush. Realistically, this is what it's going to look like. It's going to ramp up slowly until it gets to the point, which is what you want in a power supply. You don't want to set a set point of 60 volts and then it freaking spikes to, like, something a lot higher than what you want, destroying your load, your sensitive electronics, etc. All right, it's almost done. So, right, that's 100. Okay. As you can see, it looks a bit different, a bit more definite. Actually, the ripple is a lot less, and it appears to work properly. Um, but just remember, in the case for other controllers such as a buck, I keep saying controllers, converters. In terms of a buck, they're very sensitive to the capacitor values, and I much rather it's much better to just have a smaller capacitance here. I promise you it's better, because I tested this on a buck converter and it gave tremendous, there were a lot of problems that were experienced because of that. So try to go lower in the capacitance on the capacitance value, especially if you're not having a load that's switching constantly. You don't need a capacitor that's too large. So that's that. And right, I think that's about it. That's about it. Oh yes, I have to check the constant current as well. Let me just do that. Or constant current. So this is the output current. So you just go there and change the constant current. So in this case, I'd go 5.5, or let's say 5.8, or 5. No, I think 6.5 is just fine. Just do that. Run it. And obviously I have to go to the code and yes, I'm gonna be posting the link to this code. The GitHub link to this code is gonna be in the description, so you can play with it, I guess. Um, so this is for the current. So I'm gonna run that. It's exactly the same. You see, it's IREF minus I actual, and the same process. Only this time, obviously, we have different coefficients for the I. Um, the error array, different as well. The PWM input, different as well. Control max, but the maximum DT and minimum DT all the same. And obviously this as well. Well, this stays the same because it's one PWM, I guess. And the max duty obviously stays the same. And this is so important to just do it this way, so that you can move from controller to controller quite easily without changing the coefficients too much. And keep in mind, if you increase the loop execution time, I'm not saying increase, if you decrease the loop execution time, like over here, if you change this from 3 milliseconds to say 1 milliseconds, or into the microseconds, like 200 to 250 microseconds, keep in mind that these coefficients have to kind of go up. Okay, they have to go up. Let me put that comment there. Has loop execution time decreases, how do I say, as loop execution time decreases, coefficients have to increase, and vice versa. If you're gonna make the loop execution time 10 milliseconds, 20 milliseconds, which you're gonna have to do if you increase your output capacitor too much, you're gonna have to increase those, or even to some. I tried that once, 50 milliseconds. It's too much, but you have to reduce this, guys. You have to reduce them. Um, you have to reduce them. Okay, the coefficients have to decrease. how to decrease. And by the way, there are textbooks out there that actually explain how to get to these loops. Um, so if you need a formal whatever, nice control systems engineering is a good textbook for that, and actually how to calculate these coefficient values. You can go down that and check that out. It explains that how to get these coefficients. But me personally, I kind of just like to start really low and ramp my way up slowly. Takes a bit more time, but each system is different, and you just never really know what a system is like. You just never know. Even mathematically, you can calculate all day. You know, there might be a resistance somewhere that you're just not accounting for, and it just ruins your day. You know, so I prefer to just work with a system that's in front of me and sort of see what it's doing and go from there. Um, all right, so that's that. Um, okay, and let me just run that again. All right, so now the set point for the current is 6.5 amps. I'm just gonna run that. Edit properties. This will require a bit more time. Now running it to see what happens. Okay, and now I'm going back to this. Essentially the same. And so let's say you were in another microcontroller architecture and you were using 3 milliseconds. You could literally use these exact coefficients, literally these exact ones. Obviously, if your loop execution time is lower, if your timer interrupt time is lower than that, you might have to increase these slightly, or leave them as they are. Leave them as they are and follow the normal rules. I think you should do that. Leave them as they are and just follow the normal rules. Obviously, if you make the loop execution time more, you should just take them down to these values right here. Take them down to these. It's gonna take more time, but it's better that way. Because remember, you're working with real voltages and real current and real systems here. You have to take it easy, be conservative, and maybe you want to take this down to what, 6.5. I'm being really conservative with everything here because real systems, the thing blows up and it costs money, so careful, I guess. You want to take this down to 6.65. You might want to do that, or leave it at 0.8 if you're confident that your MOSFETs, IGBTs, whatever switching devices you use are not going to blow up on you. So that's that. Alright, that's that. Bunch of warnings as usual. Now we examine them. Looks like it's going to require a lot more time. So now in this case, you actually have to actually use this as an example. You're actually going to have to go up with the Ki values. So now I'm just going to make this to be 4 and 0.00428 times 3.5, and I'm going to make this 1.1498, right, because 3.5 more, because as you can see there, it's taking a bit too long because the time here is 300 milliseconds and it actually hasn't gotten to the set point yet. So I'm trying to make it get there faster. Yeah, and obviously for a battery charger system, the configuration will essentially be the same. It will look just like this. Just the code will be different. And obviously for average current mode control, the sensor is going to be over here. And for average current mode control, obviously actually, let me not talk too much about that in this particular one. Let me just limit this. But the sensor will be over here for the other type, for the other types. And yeah, the most important thing I think is the hardware, because is the hardware, and making sure the design is proper for the hardware. That's literally I'd say 80% of it, and the code is just the 20% or even less, to be honest, because this stuff that I showed right here, this is it hasn't changed. It's just always It's always been like this. It's always gonna be like this. It's not gonna change, right? But the hardware, you touch it, you don't solder something properly. Your sensors are not soldered on properly, so basically your PWM just goes to 100 all the time, or 80% in this case. So you kind of have to be careful with the hardware. You massage everything, make sure everything is operating properly, and as you can see, it gets there faster, and it's not unstable. And obviously here, as you can see, it's literally just gonna, right here, it's literally just gonna jump from 6 point whatever, that value there, to beneath that, because obviously, again, the PWM resolution is just not there. So you kind of have to be careful and take it easy with it, and yeah, and it's gonna go up and down like that, but it's okay. It's okay. It's not the best, but obviously you might want to use this on a DSP digital signal processor of any kind. Actually, there are several out there. The ones that I know are the DSP, STM, and Texas Instrument. There are others like Renesas, I think lesser known ones, but those three are the main ones that I know of, and they'll probably give you much better results than these. And obviously, the ripple that you're seeing here is as a consequence, obviously, of the size of the inductor. But try not to veer too much off of what you calculate. Not too much higher, maybe 2 max, 2.5 max. To be honest, try to keep it everything a bit safe, conservative, decent, I guess, and everything connected nicely, soldered properly. Do not spare the solder. Um, and yeah, that's about it. Maybe just a brief recap of everything. So right here in this code, you have the main loop where everything is initialized. In this case, the voltage set point is 60, current set point 6.5, I actual, V actual, and the array. And you have the array here. And now the main code, the PID code, is in the timer 1 routine. Obviously, if you want constant current, you have to only leave this out. You can't leave both of them exposed because they both affect this particular value here. Okay, your PWM. And you want voltage, uncomment this, comment this. You want current, leave this out, comment this, just as it is now. And most important things, to calculate the actual and the I actual, and obviously this as well, to reference what you already initialized in the main. I think this should be 5. This should be 5. And obviously, another important part, or you might argue the most important, your coefficient. Literally, will make or break your system. Always start small. Always start small. I know that it's gonna take time to actually get to the second, to the to get to your set point. It's going to take time to actually get to your set point, but it will get there, and you would actually have somewhere to go off of, and you would increase it slowly, and in the end you'd actually know what your system likes best. This is what my system needs, and etc. This is the coefficient that works with this particular hardware system, and etc. And obviously for the current in this example, it was too slow, so you just increase following this. So the general laws, so Ki largely affects the settling time, and the Kp largely affects stability of the system. Um, largely affects system stability. Alright, and that's that. And increase Ki and increase Kp to be at least 3.5 Ki. So every time you increase Ki, Kp has to go up as well. They cannot be too close to one another. Well, that's going to cause other issues. I actually don't know what that means theoretically. I'm sure there's a reason for that. I don't know what that is, but you do not want your Ki and Kp to be too close to one another. You want your Kp to be at least 3.5, greater than Ki. And then if you reach an unstable point, because you constantly have to increase the Kp, you don't take the Kp down. You just leave it where it's at. You take it down to where it was before. And now you increase the Ki independently. So let's say you've been increasing. Let's take this Kpi and Kii for example, right? So you've been increasing them. Now we get to this point, right? right? And this is, keep in mind, this KP is 3.5 times exactly greater than this KI value here, right? So let's say we're at this point, and or let's say we get to a point of which is like 1500, right? We get to this point and it's unstable. What do? We take it back down to what we knew before, 1498, and we leave it here, and then we start to increase this value to a point where KP is at least two times the KI, right? To at least the point where KP is 2 times AI, and then you stop there. If you're really, really desperate, you could go to 1.5 times KI. After that, you're on your own. But obviously, the PFC rules are a bit different to these, but this is strictly for DC-DC. For PF's power factor correction, that's a different system entirely, okay, with different rules for tuning. Well, different thumbs up rules anyway. And so just that's what you have to follow. You kind of have to be patient, but in the end, you have your stuff working reasonably, and no smoke. All right, so and the KD, not to worry about those. I personally, when I've tried to play around with the KD, I've had to literally increase it to crazy amounts to see any benefits, and they tend to be very temperamental. Um, not to not to give an object human qualities, but there's like a narrow range where they actually work properly, help your system, and then right after that they just cause all kinds of problems, like talking about system reaching the set point and all of a sudden oscillating, just randomly oscillating. That's what the KD does. And anyway, that's the entire system. Obviously you can find the code and modify it as you wish. um, I will not be held responsible if you modify it out of control and something, maybe it does something not so nice to your system, at your own risk, obviously. And yeah, but this the major purpose of this was essentially just to show you this is how you go about coding constant voltage to constant current control for whatever applications you need. Just in this particular scenario for this tuning rules, I'm specifically talking about DC-DC converters, specifically a boost in this case. Obviously, for a buck or any other type of converter, I encourage you, or even any other type of input voltage, output voltage, I encourage you to start from this point here. All right, and I think that's it for this video, and all the best with your applications of this, and that's it. Bye. Cheers.